this video, we'll try to see how to write the pi model of a given transistor and how to write the T model for a given transistor. Okay. So, for any given transistor, if you see, there are three different terminals, which is collector, emitter, and base. So, in the pi model, the transistor is replaced. Now, why do we write this pi model or T model? Let me tell you. We write pi model or T model for any given transistor to try to do the AC analysis. Okay, we try to do the AC analysis. I think this I told you in the previous videos. Like if you want to do the AC analysis of a given transistor to derive the equations for the various equations for different amplification parameters, we need to know how the circuit behaves for AC input when it is given. So in such cases, we need to know which would be the simplest mathematical model which we can apply so that the circuit analysis becomes very easy to do. So to do that, we have a popular model which is pi model and T model which we apply for a given transistor, which makes us to write the set of equations later for any given configuration, and that equation solution, finding out the solution becomes very simple. Okay, so what we do when we write a pi model for any transistor, what we do is we will try to write in the way which I am going to explain to you now. In pi model, the base, which I told you earlier, is replaced with the base resistance, input resistance at the base, which I derived earlier in the previous video, which is R pi. Okay. Similarly, the collector terminal is now replaced with a dependent collector current source. A dependent collector current source, which is flowing towards downwards, because I'm going to take the base terminal current is flowing downwards, so IC and IB directions are same. Now if I say this is your base terminal B and this is your collector terminal C. Now I'll mark the base current, which is an AC base current because it is AC analysis, so we normally write an AC IB, and I'll also mark the AC current small IC. And earlier, I think if you remember, we derived the formula for IC, which was GM into VBE. That is what, when I write GM into VBE, this IC equals GM into VBE, right? IC equals GM into VBE. So when I say this equation, can you say that the collector current IC is completely dependent on the base emitter voltage? So therefore, if I represent IC at the collector terminal, I should definitely use a dependent source symbol. Why? Because your collector current is dependent on the base emitter voltage VBE. That is the reason you will have a dependent source at the collector terminal. Now this both are now connected to an emitter. Okay, so this is your emitter. Now if the emitter is directly connected to ground, you will be connecting this terminal to ground, or if it is connected to some resistor, you are going to write current to resistor. Anyway, I'll keep this as in this way. So this is the emitter. Now this is the pi model for a given transistor, or you can also say this is the pi model or an hybrid model for a BJT transistor. Okay, so that is very important. Now, if I write the equation for I in this particular diagram, to write I should also mark the voltage across R pi. The voltage across R pi is nothing but the input voltage which we apply to the circuit at the base, which is nothing but the base emitter, small VB. So this was the input, right? This was the input which we saw in the previous videos. So small VB is the input voltage which is measured across the input resistance R pi. Now if I write the equation for IE, in this pi model, my IE will be equal to small ib plus small ic, right? So this is equal to the base current IE can be written as voltage multiplied by resistance, which is nothing but small VBE into R pi added with, we know that IC equals GM into VBE. So, sorry, a small mistake here, because here Ohm's law says the current is voltage by resistance, not multiplied by resistance. Anyway, here IB is what? Small VB divided by R pi, not into R pi, sorry. It is V by R. Small VB divided by R pi added with the small IC, which is GM into VB. GM into VB. Now in these two equations, I can take VB common. What I'll do is I'll take VB by R pi common completely. So in the bracket, I'll be left out with 1 plus GM into R pi. 1 plus GM into R pi. 1 plus GM into R pi. If you remember, beta by GM was equal to R pi. If you remember the R pi derivation which we did earlier in the previous video, beta by GM was equal to R pi. So I can easily say that GM into V R pi equals beta. So this will be what? This will be equal to VB by R pi into 1 plus beta. 1 plus beta. Okay, VB by R pi into 1 plus beta. So what I'll do is I'll take this 1 plus beta to the denominator. So what I'll get is small VB divided by R pi divided by 1 plus beta. I'll write in this way. R pi divided by 1 plus beta. Okay. Now this R pi divided by 1 plus beta, if you remember the relationship between R pi and RE which we did earlier, where R pi was equal to 1 plus beta times RE. 1 plus beta times RE. In the previous video, this we derived this. So I can say R pi by 1 plus beta can be written as RE. So therefore, finally, my IE equals VB divided by R pi by 1 plus beta is RE. See, this is how we generate IE in terms of VB by RE, even in the pi model when it is considered. Okay, so this is one thing which you need to know while deriving for the pi model when you are trying to consider for a BJT transistor. The one more thing which I can also say that the IC was GM into VBA. This can also be written as beta times IB. Right? IC can also be beta times IB, right? So either you can write GM into VBA in the pi model, or in the pi model you can also write the correct source value as beta times IB. If you write beta times IB, IC will be dependent on the base current IB, whereas if you write GM into VBE, the collector current will be dependent on the base emitter voltage VB. Okay, so this is what the pi model or the hybrid model of a BJT transistor. Now what we'll see is we'll try to go to T model. Okay, so let us look into a T model now. T means it should be a T shape. That is what another which I want to tell you. Why it is called as pi model? If you see this model diagram, it somewhat looks like pi symbol. That is the reason it is called as pi model. Okay, keep that in mind. Now I am going to write the T model. So let me take the transistor once again for T model. So I have a transistor. Let me take the transistor symbol once again for T model. Okay, so I have a base terminal here. I have an emitter. I have I have a collector. I have a collector here, and I do have an emitter here. Okay, fine. So in T model, the shape of T is given. Now think this is your collector terminal, and this collector terminal will now be attached to a current source, which is dependent current source. Now your base is directly given in T model in this way. So in T model, we'll try to take RE, input resistance at the emitter. That is where the T model is considered. So we'll try to take small RE. And this is your emitter. Okay, so therefore, what we do is we'll try to take small resistor, input resistance at the emitter RE. If you remember, we derived this RE in the previous video. And this will be what? A current source with GM into small VB. GM into small VB. Anyway, this is your collector current IC. This is your base current IB. And this is my emitter current small I. Right? So, I can also say instead of GM into VB, I can also say that IC equals alpha times I. Okay, IC equals alpha times I. This is also possible. This can also be possible. Alpha times I can also be possible. Now what we'll do is we'll try to write the current equation IB now. So here, if I say IB equals, IB equals IE minus IC. So this is Kirchhoff current law, which we know it, right? So IB equals, IB is entering, IC is also entering, I is leaving. So if I write just IB, then means if I write actual equation, it is IB plus IC equals IE, right? So therefore, my IB will be equal to IE minus IC. Now what is IE? IE is actually, now the base emitter voltage input voltage is across the emitter resistance RE. Okay, so keep that in mind. The input resistance is across the emitter resistance RE. Therefore, my IE will now be equal to VB by RE minus IC is GM into VB minus GM into VB. So if I take VB by RE common here, so I will take VB by RE common here. So I will be getting 1 minus GM into RE. 1 minus GM into RE. So if you remember RE model derivation, we wrote GM into RE. GM into RE as 1 minus alpha. 1 minus alpha. Because we derived GM by, alpha by GM was equal to RE. Earlier we saw this. So therefore, my alpha will now be equal to GM into RE. That is what I have substituted. Now if I write alpha in terms of beta, okay, we know that the gain alpha equals beta plus 1 by beta. This is the formula, right? Alpha equals beta divided by beta plus 1. Alpha equals beta divided by beta plus 1. Beta divided by beta plus 1. If I substitute that here in the place of alpha, I'll be able to get VB by RE into 1 minus beta divided by beta plus 1. And this will be equal to VB by RE into beta plus 1 minus beta is 1. by beta plus 1. 1 by beta plus 1. 1 by beta plus 1. Okay. So now I can write this as VB by RE into beta plus 1. And we know RE into beta plus 1. Beta plus 1 times RE is nothing but R pi. So I can say VB by R. So I can say that my value small ib equals ib equals small vb by R pi. I had a T model, I derived the value for IB in terms of R pi. I got R pi. Okay. So this is what the T model is all about. Okay. This is all about pi model and T model, which we are going to use it for any amplifier circuits to do AC analysis such that the equations can be written in a more simplest manner, and we can all, we can analyze the transistor amplifier so that we can easily find out what is the voltage gain for any given transistor. Okay. Thank you.